Hey everyone, welcome to this explainer. Today, we're diving straight into the fascinating world of the proxy design pattern. We'll be drawing directly from software developer Christopher Okrabi's fantastic analysis of the classic head-first design patterns. You know, if you've ever dealt with software that just feels sluggish because it's doing way too much heavy lifting right out of the gate, you are absolutely going to love this. We're going to unpack how introducing a clever little gatekeeper can completely transform the efficiency of your code. Okay, so here's our structured roadmap for today. We're going to cover what exactly a proxy is, the three types of proxies, the expensive object problem, the virtual proxy solution, the proxy UML blueprint, and finally, we'll get into actually coding the gatekeeper. All right, let's kick things off with section 1. What is a proxy? Adding a level of indirection. So, what exactly does a proxy do in software design? It's one of those terms we hear thrown around a lot, right? But let's pin it down to its core mechanism. The Head-First Design Patterns book formally defines the proxy pattern as a surrogate or placeholder used to explicitly control access to another underlying object. Think of it like a representative or an agent. You have an object that you really want to interact with, but instead of being allowed to just talk to it directly, you're forced to interact with the proxy, and then the proxy talks to the object for you. This illustrates the core concept brilliantly. We're introducing a level of indirection. In the top scenario, you just call the thing you want directly. But down in the proxy route, you call a completely different entity that acts on your behalf. Now, you might be wondering, why in the world would I intentionally put an obstacle between me and the object I want? Well, that all comes down to intent. Which brings us to section 2, the three types of proxies: remote, virtual, and protection.
You see, there are different intents for wanting to control this access. The structural code might look incredibly similar for all of them, but the reason why you're using them is what sets them apart. The source material outlines three main types. First up, we've got remote proxies. This is for when the real resource exists somewhere completely different, like on another server. The proxy handles all that messy networking stuff, keeping your local code clean. Second is the protection proxy. This one acts like a bouncer, literally checking user access rights before allowing a method call to go through. And third, we have the virtual proxy, which focuses on managing heavily demanding resources that you really don't want to load unless absolutely necessary.
Now, the crucial point we're going to focus on today is that third one, the virtual proxy. It acts as the ultimate gatekeeper, making sure you only incur those heavy memory or computation costs when it is absolutely required by the user. The whole shebang here is about lazy evaluation rather than eager evaluation.
Moving on to section 3, the expensive object problem, or the danger of premature optimization. To really appreciate the proxy solution, we first need to feel the pain of the problem. Imagine an application that frequently instantiates objects that just eat up massive amounts of memory. Imagine it doing this even when the client isn't even asking for the data yet. We're literally just burning through processing power and melting our servers for absolutely no reason. For example, let's say we have a book parser class. We pass a massive string like the entire text of a ridiculously thick book right into its constructor. And the moment it's instantiated, bam, it instantly does all this heavy computation to figure out page counts, text complexity, word types, you name it. It pre-calculates everything so it's ready to go. Because of all that pre-calculation, the actual string parsing during instantiation is an intensely heavy performance hit. However, later on, asking it for the number of pages is just a rapid, cheap, split-second method call. But what if we instantiate this book parser in our app, and the user never actually asked for the page count? Well, we've just wasted all that processing power. There's got to be a way to delay that expensive parsing until the exact moment the client actually requests the data. That leads us nicely into section 4, the virtual proxy solution deferring the heavy lifting. So how do we fix this without having to rewrite the original expensive parser? Actually, let's say that parser is a third-party library. We literally can't touch its code, but we can change how we interact with it. We solve this by switching our strategy. We move away from eager evaluation, where we just blindly pay the computation cost up front the second we create the object. Instead, we embrace lazy evaluation, managed by our smart proxy gatekeeper. The proxy steps in to stand in for the parser, and it flat out refuses to do any hard work until it's absolutely forced to. Now notice the absolutely crucial rule of this pattern highlighted in the quote here. A proxy must look exactly like the real resource to the client. It doesn't change the interface at all. If the client expects a book parser, the proxy has to behave exactly like a book parser.
This substitutability, it's a mouthful, but it's key. That is what allows us to swap the real, heavy object out for our lightweight proxy without breaking the rest of our application's code.
Okay, let's look at Section 5, the Proxy UML Blueprint, Structuring the Pattern.
Let's formally map this architecture out to see what makes that swapping possible. The blueprint requires an interface, let's call it iSubject, that dictates the shared methods. Both our heavy, expensive real subject and our lightweight proxy agree to implement this exact same interface. The crucial difference, the proxy uniquely holds a hidden private reference variable pointing to a real subject. This is exactly what allows the proxy to eventually delegate the real work to the actual object later down the line.
And finally, Section 6, Coding the Gatekeeper, where we write the actual proxy logic.
Let's translate that blueprint into concrete code execution. First things first, we establish our interface. Both our real book parser and our new lazy book parser proxy agree to implement the iBook parser interface. This guarantees to the client that no matter which one they're holding, they can safely call the getNumPages method. The client is blissfully unaware that a proxy has even been slipped into the mix. And right here is where the magic happens. When the client creates our proxy, they pass in that massive heavy book string. But inside the proxy's constructor, we simply save that string to a variable. That's literally it. We actively avoid computation by explicitly setting the reference to the actual parser to null. Boom! We've created an object instantly, entirely bypassing the heavy performance hit of parsing.
So here is the lazy evaluation in action. At some point later, the client finally requests the page count, and the proxy springs into action. First, it checks, hey, is my internal real parser still null? If yes, it finally takes that massive string it saved earlier and instantiates the real book parser, taking the performance hit only because it absolutely has to. Then it delegates the page count request to that newly created real parser and hands the integer back to the client. Plus, and this is a real game changer, for any future calls, the real parser is already built and cached inside the proxy.
As we wrap up this explainer, I'm going to leave you with a bit of a challenge. Take a hard look at your own code bases today. Are you blindly instantiating massive objects or pulling huge database queries before the user even needs them? Ask yourself, where can a virtual proxy act as your ultimate gatekeeper to drastically speed up load times, save resources, and just keep your servers from breaking a sweat? Thanks so much for joining me, and I'll